Okay, so this is the second section for the chapter 6. Here we're going to learn about another type of work that is called pressure and volume work. Meaning, if the pressure is given and then we have a change in the volume, how can we find out the work for that? Okay, normally this applies for gases, pressure volume work. Expanding gas, pushing back the atmosphere does PV work. Now look at this example over here. There is a movable piston. Okay, and this is your system. System has gases. And then if the gas expands, gas can expand as the temperature increases. So the gas can expand against the external pressure. So now the system has become more volume. So here you have initially you have a certain amount of volume. Now this volume has changed. So we can find out the changed volume called the delta V. Delta again represent the change, okay, change in volume. That would be final minus the initial. Now this is happening against a constant external pressure. So the pressure exerting from the atmosphere, we can represent it as P. Okay, so we can find out the work done by the system by this equation. That's going to be W equals negative P delta V. P is the external pressure and delta V is going to be the change in the volume. Now in this case, who is doing the work? Is the system doing the work or the surrounding doing the work? System is doing the work against the constant pressure. So system is losing work or gaining work, losing energy or gaining energy. System is losing energy, right? If the system loses energy, what should be the sign of W? It has to be negative. So to indicate that, the equation itself has a negative sign saying P delta V, because the pressure going to be external pressure. Delta V, if the system is expanding and then the volume is becoming increasing, what's going to be the delta V? This is going to be higher volume compared to this one, larger minus smaller volume. Delta V going to be positive. Pressure is positive. So we are getting a positive value if you don't have this negative right there. But the system is losing energy as work. So to indicate that, we have W equals negative P delta V. Okay. Now let's look at an example. A reaction taking place in a container with a piston cylinder assembly, just like what we saw in the last slide, at constant temperature. Temperature doesn't change, but it is expanding. The gas is expanding by itself. Constant temperature produces a gas and the volume increases. A reaction taking place in a container, just like maybe burning of a hydrocarbon, but with oxygen, it can burn by itself. So it can producing a gas at the same temperature, and the volume increases from 125 milliliters to 652 milliliters. So we are given the initial volume and the final volume. So we can find out the delta V against an external pressure 988 torr. Calculate the work done in joules and 180 m liters. And we are given conversion factor 1 atm liter equals 101.3 joules. Okay, so the ATM is atmosphere, that is a unit that we measure pressure. Liters is the unit that we measure volume. Okay, so we want to make sure we convert our volume to liters, and also we convert our pressure is given in torr 988. We need to convert it to ATM. So remember, we are going to use this equation W equals negative P delta V. Now the pressure is given in torr, and 760 torr equals 1 atm. So we can use this conversion to convert 988 torr to atm. So then 988 torr, how do you convert it to atm? 760 torr equals 1 atm. This will give us the pressure in atm. And then the volume. So we want to find out the delta V, which is volume final minus volume initial. What's the final volume? 652 milliliters. And then initial volume 125 milliliters. Okay. What's that going to be? 7. I'm just going to look at there. 527. Okay. 527 milliliters. But we need it in liters. How do you convert 527 milliliters to liters? So we use 1000 milliliters equals 1 liter, which is 0.527 liters. And then the pressure, when you convert it to atm, it would be 1.30. Okay, it would be 1.30 atm. Now that is pressure. We found the volume delta V 0.527, and we can use this equation W equals negative P delta V. So the pressure is going to be 1.3 atm, and then the volume 0.527 liters. So we're going to multiply those together. So we can see the work over here. It's just showing how to calculate the delta V, which I did with you guys. And then converting to atm, we did that too. And then W, now we have atm and liters. W, P delta V, negative P delta V. Pressure is 1.30. We have to carry that negative sign, 1.30 atm times the volume 0.527 liters. Multiply the two, you get the answer 0.685 atmosphere liter, negative. But in our question, it is asking us to get it in joule. So from W equals negative P delta V, you're going to get the answer in atm liters, and then you use this conversion to convert it to joules. You take that 0.685 atm liters in negative. 1 atm liter equals 101.3 joules. So you have to multiply these two to make it to joules. Negative 69.4. That's how we use P delta V, negative P delta V, to find out the work done by the system. Okay. Okay, enthalpy. Now we talk about energy. Energy could be a combination of Q and W. Now what is enthalpy? Enthalpy is also a form of energy, but we call it a chemical change at constant pressure. If the pressure is constant, the change in energy is given the name enthalpy. Okay. Now we learn earlier delta E, energy equals Q plus W. To determine the delta E, both heat and work must be measured. Okay. And then the most common chemical work. So most common chemical work is pressure volume work. We saw that also. And pressure volume work mainly involved for gases. Okay. The most common chemical work is PV work, which is the work done when the volume of a system changes in the presence of an external pressure. Enthalpy, H, given the symbol H, is defined as energy plus the pressure volume work. Okay, so enthalpy is, this is how the enthalpy is defined. So we can say delta H, change in enthalpy, equals change in energy delta E plus the delta PV. Okay, if a system remains at constant pressure, now you take this form, delta PV, meaning change in pressure and change in volume. Delta, when you have it at the front, meaning changing pressure and change in volume. But if a system remain at constant pressure, if the pressure is constant, final pressure minus initial fresh pressure, what's the going to be? What is it going to be? It's going to be 0. So the delta P is going to be 0, right? If the pressure doesn't change. And if the volume doesn't change much either, like let's say your final volume minus initial volume, but there is not much of a change. So then what's happened to the delta V? That's also going to be 0. So if a system remains at constant pressure and its volume does not change much, meaning this delta PV term become 0. So in that case, we can come up with this equation where delta H equals delta E. So enthalpy is basically energy, delta E at constant pressure and when the volume doesn't change much. Okay. Delta H as a measure of delta E. Delta H is a change in heat for a system at constant pressure. Remember, we talk about delta E is the sum of Q plus W. Okay, if the W work as negative P delta V and it became 0, so then the delta H is a change in heat for a system at constant pressure. Let's see how it comes. Now QP is the heat at constant pressure. QP equals delta E plus pressure volume work P delta V. Since it's happening at the constant pressure, that's going to be delta H. Okay, that's delta H. And then delta H is going to be equals to delta E if this is going to be 0. So at constant pressure, delta H, which is the enthalpy, is same as delta E, meaning it's the heat. Delta is a change of heat of a system. You can see here delta H is the change in heat for a system at constant pressure. Change in heat. Okay. And this is applicable for reactions that do not involve gases. If it involves gases, then we have this pressure volume work. This also involves for reactions in which the total number of moles of gas does not change. Even if you have a gaseous reaction happening, but if the number of moles doesn't change, then the volume will not change. Okay. And then for reactions in which QP, this term is much larger than the P delta V. Even if you have a small amount of P delta V happening, but the QP is much larger, you can neglect the amount coming from P delta V. Okay, for reactions in which QP is much larger than P delta V, even if the total number of moles of gas does change. So with these assumptions, we can assume delta H equals delta E. Now this example shows enthalpy of exothermic and endothermic processes. Now we are learning two terms, exothermic and endothermic. You may have heard these terms before, but let's look at them, what they mean. Exo means outside, endo means towards. Okay, exothermic. Exothermic means, thermic means heat. Heat is released to the surrounding. And endothermic mean, again thermic is heat, endo mean taking inside, endothermic. So heat is absorbed by the system, endothermic, heat is released by the system, exothermic process. Now let's say here we have a hydrocarbon, methane plus oxygen, CH4 plus 2 oxygen giving us carbon dioxide and water, combustion reaction of methane. Now when the reaction is taking place, okay, the heat is generated. You can see that if you have a gas, you burn it and then it is releasing heat to the out. So the product has less enthalpy compared to the initial enthalpy. This is the initial amount, this is the final amount. So heat is being released to the surrounding. What do you call this? Is it an exothermic reaction or an endothermic reaction? If the heat is released, that is called an exothermic reaction. Okay, heat is out, exothermic reaction. So then final state has less energy. What about the delta H? Final is less compared to the initial. So final minus initial would be negative. So the delta H for exothermic process is going to be less than 0, which is minus. For example, let's say initially you have a amount of energy 20, and then you final energy you have about 10. So the delta H is going to be H final minus H initial. What's the final amount? 10. What's the initial amount? 20. So 10 minus 20, negative 10. So in an exothermic reaction, you release heat to the out, and then the delta H would be negative value. Delta H is going to be less than 0. And then what about in an endothermic reaction? So for example, here you have solid water. What is solid water? Solid water is basically ice. You keep ice on your table, and what happens after a while? It can melt. When ice is melt, does it need to absorb heat from the surrounding, or does it going to lose heat to the surrounding? It need to absorb heat, and then only it can warm up to become liquid water. So heat is in, and that is endothermic process. Now the final energy, final enthalpy has more compared to the initial. So the final minus initial would be positive. So the delta H would be greater than 0. Okay. So in an endothermic process, let's say delta H. Let's say initially you have 10, and now finally it has gained energy 20. So 20 minus 10 is positive 10. So for an endothermic process, delta H is going to be positive, greater than 0. For an exothermic process, delta H is negative because it's releasing. Okay, since the heat is out, you can consider the heat. In an exothermic process, heat is released, so you can consider heat as a product. In an endothermic process, you can consider heat as a reactant. Okay. In each of the following cases, determine the sign of delta H. State whether the reaction is exothermic or endothermic, and draw an enthalpy diagram. Okay. So what's given here? There are some stuff missing. Hydrogen in the gaseous state plus half oxygen gas, giving you liquid water plus 285.8 kilojoules, and then the other one 40.7 kilojoules plus liquid water, giving you gaseous water. Now in these two cases, the first one, hydrogen with oxygen, half oxygen giving you liquid water, plus 285.8 kilojoules. The next one, liquid water plus this amount of heat giving you gaseous water. Okay, it's asking, determine the sign of delta H. State whether it is exothermic or endothermic. Now, what do you think about the sign of delta H? Who has more energy in this case? So here, heat is a product. You see here this plus 285.8 kilojoule, heat is measured in units kilojoule, so heat is a product. If heat is a product, has the heat released or has the heat absorbed? It's released. So the heat is released. So if the heat is released to the outside, what should be the sign of delta H? So your reactant has lost energy, meaning it's going to be, the sign of the delta H is going to be negative. Delta H going to be negative. The sign of delta H going to be negative. And this amount is the heat released. Okay, delta H is negative. So then is it exothermic or endothermic? That is exothermic reaction, the first one, right? And in the next page, we will draw the energy diagram. So what about the second one, B? For the B, liquid water becoming gaseous water. Do you find the heat in the reactant side or the product side? Heat is a reactant, meaning for this reaction to take place, heat is being absorbed. If the heat is being absorbed, what is the sign of the delta H? Who is going to have more heat at the end? Gaseous water. So the final would be higher in energy compared to the initial. So the sign of delta H is going to be positive. So for the B, delta H going to be positive, and then it's been absorbed, the heat is being absorbed, so that is an endothermic reaction. Okay, now let's look at the other page to see the energy diagram. Okay, so heat is product on the right, so delta H going to be less than 0 and the reaction is exothermic. So these are the reactants, hydrogen gas and oxygen reactants. It loses negative 285.8 kilojoules, exothermic reaction. So this is the product. Product has more energy compared to the reactants. It's you losing this much of energy. And then the second one, liquid water becoming gaseous water. In order for the liquid to boil off and make some gaseous water, it need heat from the surrounding. The amount we need to give is 40.7 endothermic reaction, and delta H is positive. Okay. We'll start the calorimetry in the next